Hello students, welcome to lecture of Kinematics and Theory of Machine. We are going to continue gear today, and topic we will cover in this lecture will be law of gearing and forms of teeth. There are two types of form, and also comparison is there. So we will cover these two topics today. Let's start. Okay, let's start law of gearing. This is the derivation and this figure and statement. We will derive this derivation, and we come to this statement, but it is very easy. Only have to understand the geometrical relation between two gears and this figure. So we are going to step by step. Okay, check this. Two gears I have taken, and their center is O1 and O2. We have connected both the center with this line. Okay, so you can see the contact point between these two gear. Okay, let's name it O1 and O2 are center of two gears, and it they are rotating with omega 1 and omega 2 velocity. So Q is a point, contact point. Now we are making a tangent at a contact point. So common tangent at a contact surface will be TD. It is a common tangent, and you know that you have already done in EG. At a tangent you also can make what? Normal. So it is a tangent and normal at a Q. Q is a contact point between the teeth. So now we are making the normal to common normal from O1 and O2, and let's name it M and N. So here you can see on a figure that TT is a common tangent, and MN is a normal to the surface contact Q. Okay, so Q is a point which can be considered as a O1 gear 1 and gear 2 both. Okay, so we can connect contact point Q to gear 1 and gear 2. So you can see here these two lines means this line QO2 and MN making some angle, and same as O1Q and O1M making some angle. Let's name it M and N. Okay, so alpha and beta. So you can see here this angle is a alpha, and here second angle is a beta. So Q is a common point, and means Q is a moving, so velocity of Q can be considered with respect to both gear, because it is a contact point. You can consider as on both at a time, this second. Okay, so so now consider on a gear 1. So this is the velocity of Q with respect to gear 1 V1, and you can see this and here. What will be the angle? What will be here the angle? So I have said in starting, it is a totally geometrical relation you have to find. If there is a 90 angle here, it is a alpha here, so this will be 90 minus alpha, and you can see this is the 90 angle, so this will be directly alpha. Okay, same angle, and same Q point we can consider on a O2. Velocity will be V2. V2 will be perpendicular to O2Q. Okay, velocity is always perpendicular to this, so same angle will become beta. So alpha, same angle alpha has become here, and beta on gear 2 will be made here. So this is the velocity V1 and V2. Now makes here the triangle, means we draw the normal line on MN, and you can see there is a triangle, velocity triangle QED. velocity triangle QED. Okay, so first you can see V1 cos alpha, V2 cos beta. Now you have to understand what is the V1. V1 is a velocity. So for that I am going to explain it. If any link, like consider this is the A and this is the B. If AB link is rotating in this direction and we have to find the velocity of B, what will be velocity of B? Means we have to find the V1 and it has a angular velocity omega 1. So remember that always linear velocity V1 is equal to will be angular velocity omega into distance between this point, reference point, and point for which you are finding the velocity A, B. Okay, so linear velocity is equal to omega AB. But in our case, what will happen? V1 means velocity V1. What will be the velocity V1? Is equal to angular velocity omega into distance, this distance. So check this out, omega into O1q cos alpha, and same as for V2 velocity. V2 velocity is equal to angular velocity of that gear, and from O2 to that point, distance of this point means this. Okay, so this is the O2, omega 2 into O2q. So next, what is the cos alpha and cos beta? You can consider this triangle. Check this, I am giving you some heat so you can find this triangle O1MQ, and there is a alpha. If you see that cos alpha here, cos alpha, find the cos alpha, and same as triangle, you can see O2QN, and here you can see this is the angle here, this beta angle. So you have to find again cos beta. So O1 into O1Q into cos alpha will be become O1M upon O1Q, and so here O1Q will be eliminated and remain O1 into O1M and O2 into O2N. So here the final result, omega 1 upon omega 2 is equal to O2N upon O1M. So if you want the omega 1 upon omega 2 constant, means constant angular ratio, so what you need to make constant? O2N upon O1M. Right now see the O2N means which distance? You can see O2N means this distance. Okay, and O1M is this distance, and you can't make sure that this distance, this ratio will be always be constant. So if you want to derive, there is a in here for constant ratio. Check this. We have to consider pitch point, because pitch point is a, you can see in figure right now, pitch point here. This is a point between point of contact of pitch circles, which is always remain at a steady place at a point of contact. So this is the common normal, which intersecting the two center lines, and we have considered as that pitch point right now. Okay, so what will happen if you consider this triangle, triangle number 1 is a O1MP, and triangle number 2 O1MQ. As this both in both triangle, two sides are common, so as a similar triangle rule, you can say that O2N upon O1M is equal to O2P upon O1P. Okay, so you have derived the final statement O1 upon O2 is equal to O2N upon O1M is equal to O2P upon O1P. So I am explaining why we have to, this is okay up to this point, why we have introduced the pitch point here, because pitch point is a that point will remain at the same place. So if you want to prove that this ratio will remain always constant, we introduce the pitch point and find that relation. Okay, so now time to statement of the law of gearing. So this is the law statement for the law of gearing. Okay, now we are going to the statement. On statement, so check this: the common normal at a point of contact between the pair of teeth must always pass through the pitch point. You can see common normal. Okay, common, this is the common normal. This common normal must pass through always from this pitch point here. Otherwise you can't say omega 1 upon omega 2 will remain constant. This ratio remain constant because it passed through the pitch point P, and we have derived that here O2P upon O1P. So if P point will be here and if normal pass through the pitch point, you can say that this ratio will remain constant and gear will give constant velocity ratio. So remember that common normal at a point of contact must pass through the pitch point. Let's see, let's learn this by animation. Okay, you can see here, first of all you have to understand where is the pitch point. Check this, you can see here it is a pitch point. How you can know where is a pitch point? Check this, when this is the pitch circle of gear O1, this is the pitch circle of gear O2. Okay, all points are moving, but pitch point is a contact point between the two pitch circle. It will remain always here, it is not moving. It is the point of contact between the pitch circle. So common normal always must pass through the pitch point, means gear is moving, point of contact between two teeth is moving, but normal is, you can see, always pass through the pitch point. And the statement for the law of gearing is the common normal at a point of contact between the pair always must pass through the pitch point. And it is okay. That's it for the law of gearing, and we are going to move the next point. It is a form of teeth. There are two types of teeth mostly, cycloidal and involute. So first check the cycloidal. You already seen this cycloidal type profile also in EG. Remember, try to memorize that. What is cycloidal? In cycloidal, you know that the cylindrical part rotating on a straight surface, and if you locate the point, it make the curve. It is known as a cycloidal curve. And if cylindrical part move along the any circular part, then makes it a epicycloid. And if it is inside of that circle, it is a hypocycloid. So this is the epicycloid and this is a hypocycloid. And using that that profile, using this profile, you manufacturing the, if you designing the teeth, then it is known as a cycloidal teeth. You can see here one circle is make, and when this circle is rotating, you got this portion only. And same as in bottom at a pitch circle, you making a rotating another circle, and due to that rotation you got this part. And same as at this point, this circle will rotate opposite direction, and if you rotate, total curvature is that, but you use only up to this point. So like this is epicycloid, this is epicycloid, and these bottom parts are hypocycloid, and that's how we get the profile for the cycloidal teeth. Involute teeth, you also learn this profile in a EG. Involute curve, you know that if any string is put it around this any circular, and we open this string, this curve we get. And getting this curve, from this curve if we making any profile, then it is for gear, it is known as a involute. Okay, so check this out. From this curve you are using one side of teeth, and this is the top length, and again same, but you can say a mirror type, you again getting another curve from this side. Like in this figure you have seen already that this is first curve, and if you making the second curve in from this form in that direction and make the land here, so you can get the teeth here. This is the profile for the teeth. Okay, so it is a involute teeth.